Welcome to lesson 12, conventional current. So the idea of lesson 12 is we're going to be able to explain how moving charge creates a current. And we're going to talk about what current means, how to calculate current. I'm then going to talk briefly about at the end, sort of what the homework is, and then that's going to be pretty much the lesson. So thank you. Let's quickly go back to what we did last time. Last time we did an introduction, history of electricity. I've changed the title of this lesson because the old one didn't make any sense, but don't worry about that. So what we were doing is we talked about how current can be generated by rubbing essentially amber that creates a charge. Ultimately, this is sort of what I've been using to describe to my year 11s. I said ultimately the fur rubs off the electrons. Think of the fur as a bit of a broom, if you will. That's the word I could not remember. And it's got lots of fibers on it, and the fibers sweep off all the electrons. And I like that analogy because that's essentially what happens, because then the amber stays positively charged, whereas the wool or fur becomes negatively charged. And then you can use that positive charge to attract people's hair, water, small pieces of feathers, etc. I talked about the Leyden jar, how that stores electricity, and then talked about how the voltage pile, how that's just a big old battery. Some voltage piles that are really big and old are actually still creating charge. They're still creating current because they were built really industrial size, and it's kind of cool. And I said this main idea here, and this is the takeaway. Electricity is the process in which charged particles, usually electrons, are moved from one location to another. Why the electrons? Because the protons and the nucleus are just too big to move. The electrons are free to move. Let's talk about now what that means. We said why the electrons move. Overall, the reason why electrons move is because electrons, they will start off at a place with a negative charge, and they will want to get to a place with a positive charge. They want to move from one place to another to balance out the charge, because electrons attract the positive charges. Let's talk about now how this relates to conventional current. We did actually talk about this guy here, Charles Coulomb. We said that he measured coulombs being C, and he said that they have a charge of Q. We said that 1.6 times the negative 19 is the charge of one electron. It's a very, very small charge. In fact, you need to have a lot of electrons to get to a decent amount of charge. How many coulombs of charge would you need? If you had 2 coulombs, we just multiply by 2. 6.2 times 10 to the 23, we multiplied it, and for the last one, we divided it. If you don't know how to do that, go back to the last lesson. But now we're going to talk about Andre Ampere. Now this dude here, he was a French scientist, and what he came up with is he came up with a new way to explore this idea. What he did is he said current is the flow of electricity and has the symbol I. Now, the symbol I think there's no general consensus why I chose I, but I think it comes from the Latin word imperatus, which means to move, so it makes sense. It is measured in amperes or amps. That's why we would say 20 amps, 3 milliamps. We usually just shorten that to amps, but you can write down amperes if you want. This slide's got a pencil on it, so later, either today or later on, I want you to copy this down somewhere in your notes, because it's going to become useful later on. And this is now where the formula comes in. 1 amp is 1 coulomb per second. So it's sort of got to do with speed. It's got to do with how quickly something moves. So this formula here, I equals Q over T, is the formula for calculating the current of something. The current is the charge divided by the time, or how long it takes. If you've got 1 coulomb going every second, you've got an amp. If you've got 1 coulomb going every 2 seconds, then you've got half an amp. That means you've got like half a coulomb each second. Let's deal with some basics here. 22 coulombs of charge passed down a wire in 8 seconds. What's the current? Can I get someone to either shout out the answer or put it in the chat? Either or. I'm going to do it now because I can. I'm not going to tell you the answer. I'm waiting for someone.
2.75.
Wait, no, I've read the question wrong.
2.75, correct. So what you would do is you would go I equals Q over T, Q being the charge, which we know is 22 coulombs. We know that T is time at 8 seconds. That's going to give you 2.75 amps. Now I can just write A for amps. Okay, so that's one way to do it. Okay, that's pretty much how you would do it. We could also rearrange that formula to find out how much charge goes in a certain amount of time. Okay, cool. Next, how many electrons pass through in 1 second? Well, if we now know that, let's figure out if the amount of coulombs that pass through in 1 second. The amount of charge that passes through in 1 second is going to be I times T. If you don't know how I got to that, what I would do is I'd say I equals Q over T. I'm going to multiply both sides by T. That gives me I equals Q times T. If I have 2.75 amps times 1 second, that's going to be 2.75 coulombs. But that's not what the question's asking for. The question's not asking for the amount of coulombs, it's asking for the amount of electrons. But if you go back, we know that one electron is 1.6 times 10 to the negative 19 coulombs. So if I have 2.75 coulombs, I'm just going to say, well, how many 1.6 times 10 to the negative 19s fit into that 2.75? And I can do that on my calculator, which I'm going to do now. I'd suggest you guys do that as well on your calculators. If you don't have a calculator, you need to start bringing one to a desk, or you can pop open a separate window. I got 1.72 times 10 to the power of 19 electrons. I'd love for someone else to confirm that, either in chat or somewhere else. Is that some, or they can say it out loud. Is that what you guys got? Something like that?
Yeah.
Yep, yeah. That's what you got. Thanks. And Thomas got the same thing. Beautiful. Thanks, Kevin. All right, beautiful. So that's how you can use current. So now we've got an idea of, okay, current is just how much charge is moving in a particular time. If you've got a lot of charge, that means it's almost like got to do with the speed of something, how quickly the flow of something's going. If you've got a lot of charge or a lot of electrons moving in a very, very short time, you've got a high current. So I might put that here. Lots of charge, oops, over a small time equals high current. But if you have, of course, the opposite would be little charge. So just a little bit of charge over a long time. That's going to give you a low current. And so those are the two ways that we've got different things here. What the next part of the rest of the lesson though is trying to explore what this idea of current sort of means. I've got 23 minutes left. So let's talk about current now. The next couple of slides are just sort of, what does it mean? In this case, I've got a, I'm just going to try and link the idea of current to the idea of flow. Of current sort of links with this idea of flow, or how quickly something flows. Usually we're going to use a river. In this case, we're going to use plumbing. So here we've got a big tank of water. We're going to call this tank is like a battery. Remember, a battery in a circuit is where we hold all our charge. It's all where we hold all our energy. It's the same thing. This pipe is going to be like a wire. It's like a wire. The tap is like a switch. When the tap is off, is there any flow? Is there any quick open question? When the tap is off, can you guys see any water flowing?
No.
Nope. Beautiful. Thanks, Dina. Yep. No flow. No current. Done. Perfect. If I open this tap up, right, suddenly there's a big flow of water. Okay. Is there any current then?
Yeah.
Yep. Thanks. Thanks, Dina. No, it's Jason that said yes. I'm sorry, Jason. Got you confused. Yeah, there is a flow of water going down now. That means there is current. So when the switch is closed, there is no current. There is no movement. There is no flow. In order for there to be a flow or a current or a movement of charge, you need to have the switch open. So what does that mean for a regular circuit? A regular circuit, if the switch is off, there is no flow. When the switch is on, there is a flow, there is a current. And we're going to keep referring to current in this way. Current we're going to refer to as the flow. Actually, you know what? Let's take this to the next level. Current is like the flow of a river. Okay, and I've actually spent time changing my color to blue. The bigger the river, the higher the current. If you've just got a little stream going, you've got a low current. And of course, if you've got like a brick wall blocking your stream, then there's going to be no current because you are blocking it. And that's what a switch does in these situations. What else can we talk about when we talk about charge and circuits and electricity? So here's a quick question. Would this work? Would this make the light bulb light up? If I had a wire, imagine this wire is actually connected to the top of this thing, and it's connected to the bottom of the battery. I've got an answer from Bao, who says nope. Also Emery that says no. Hey, welcome Emery, I haven't seen you in a while. So yeah, no, this isn't going to conduct electricity. Can I get someone to say why? Oh, there's no cycle for electrons to move. Thanks, Jason. Good answer. There's no cycle. Okay, all right, what if I do this then? Is there a cycle now? Will this work? Yes, Jason says yes. So does, can't read who that was. So does Angus says yes 20 times. Actually, Angus, you're wrong. No, this won't conduct electricity. So get that. It's a bit weird. Let's see why this doesn't conduct electricity. The reason this doesn't conduct electricity is because, yeah, sure, you're right. It looks like it will because it's got a circuit, but this is the positive end of the battery. Well, this is like, even if this was the negative end of the battery, there's no reason. The electrons might want to move down here, but there's no reasons for them to want to go back up. There's no circuit. You need to have a positive and a negative end. Okay, so then that's what I was saying. Who's saying that? Faulty. Aaron's like complaining about something. Cool. So this one, would this one work? Yep, there it is. Thanks, Weiss. Yeah, it's kind of like double side. So let's have a look at this one. Yes, this would work. Why? Charge must move in a cycle that allows the negative charge to move to the positive. Grab a look at this. Now, it doesn't really matter which end of the battery is negative or positive, but if this was the negative end, now the electrons can go through the light bulb and then through this wire to get back to the negative end of the battery. So you can actually create a circuit. One of the reasons why I love, and of course, why the electron's moving is because they want to get to the positive end. They will go through a light globe to get to that positive end of the battery. And the reason that they move through that light bulb is because they're attracted to it. Yeah, just keep swimming. You got it. Okay, so next. So yeah, the charge must move in a cycle. So we've got these two things about circuits so far. Essentially about current. Current can't be blocked. Current needs a path. And it also needs to move from positive. It needs a path, and it also needs to have a negative and a positive. Otherwise, it has no reason to move. Okay? And then once we get that charge moving, then we've got current. Okay. So let's talk about electron movement. Now, I find this slide really interesting because it actually sort of breaks down a really big myth about circuits, and essentially about current. Electrons don't actually move very far in a wire. The circuit is simply how quickly the charge is passed down a wire. And this is one of the breakdowns in the, this is one of the reasons why our theory breaks down. Okay. Is there a lifespan? There's no real lifespan of electrons. They just they can live forever. But the idea is this: when we talk about a river, or when we talk about electrons, people usually think, oh, well, obviously current is like, they think about two big wires, they think of electrons, and these electrons are like, they think of them as in tubes, and they just shoot down these tubes. To a degree, that's right, but also it's not. Because if you look at these electrons here, you can see, right, as they move, I'm not sure if you can see my mouse, but as they move from one to the other, the electrons don't actually move very far. They only move like one space. But if you look, the overall direction, the electrons actually moving pretty quickly. They are moving one atom per time to the left. They are still moving. The charge is moving. And how you can tell the charge is moving is by, instead of watching the electrons jumping, watch the positive charge move from left to right. Watch that current as the charge moves from left to right. It moves pretty quickly. So overall, it can take like sometimes between like hours to, you know, it can take somewhere between hours to days for an electron to travel down a wire from the, you know, cord in your PowerPoint all the way up to your light bulb in your lamp. But that's the idea, is like, it's not the charge, it's not the electrons that we're worrying about. It's actually the movement of charge. So this is a bit of a weird concept, but I think it's actually a really good way to sort of make sure you understand the electron. It's not like a pipe. It's not like a pipe that it's not a pipe that electrons are racing down. It's like because ultimately that's what, if you open up a wire, it's a lump of copper. It is then solid. It's just these electrons are moving atom from atom every so often. Any questions about that? This is one of the more tricky concepts. No? No questions? I'm going to keep going. If you want to come back to this later on, so maybe rewatch this section, you can. If you want to look this up later on, because if you don't understand, I would suggest you look up something called electron drift, because that's what this is actually technically called. I only found out that's what technically called this year. It's called electron drift. The electrons don't actually rush down like a pipe. They just move from atom to atom. It's the charge that moves a lot. That's why when we talk about current, we talk about charge movement, not about individual electrons. Speaking about individual electrons, let's talk about this. Now, there are two types of current. Conventional current. Now, conventional current assumes that current flows out of the positive of the battery through the circuit and back to the negative side of the battery. So out of the positive and through the negative. This was the convention established when electricity was first discovered. It is incorrect though. Like when we first discovered electricity, this is the one that we first thought about it was, because we thought the positive charges were moving up the negative charges. Electron flow is a different way to draw current. Electron flow is what actually happens. The electrons flow out of the negative side of the battery and go into the positive side of the battery. Now, a quick question for you guys. I want to see a vote here. Which one do you think that engineers use? Do you guys think they use conventional current, or do you guys think they use electron flow? Throw your votes either in the chat or you can say them out loud. What do you got? What do you think, Angus? Are you still there? Do you think electron flow or conventional current?
I think conventional.
Yeah. What about you, Marco? Are you on audio or are you somewhere else?
I'm on audio.
Okay. What do you think? Conventional or electron flow?
Conventional.
Conventional. Okay. All right.
Twinsies.
And what does chat say? Vincent says conventional. Emery says conventional. Beautiful.
I want to talk to you, sir.
The idea is, even though it's I find this really interesting, even though a conventional current is wrong, right? The directional current, it's not the one that we use. It is the one that we use. Technically, it's wrong because the positive charges don't move. The direction the current flows does not affect the circuit and what the current is doing. Thus, it doesn't make much of a difference, which convention you use, as long as you're consistent. Both conventional current and electron flow are used but in general, the science disciplines use electron flow, whereas engineering disciplines use conventional current. This is an engineering course, so we're going to be using conventional current. It's a bit weird that we use a form of current that is technically wrong, but this is, I guess, the reason why, because it doesn't matter. Ultimately, if you wire up a circuit, with a switch and a light bulb, it doesn't matter if you connect the light bulb to the positive end or the negative end, because it doesn't really matter. The electrons are going to travel through it no matter what. There are some things that it will make a difference for, but for us, most of the time, it doesn't make a difference. The only time you might use electron flow might be if you're talking about like chemical reactions like electroplating, or whether you're trying to fire electrons at a screen to make a TV. That's when you might have the main differences here. But in general, yeah, so we use conventional current even though technically it's not the way that the electrons are moving. We use conventional current even though it's technically wrong. So it's kind of weird. I think it's interesting though. So the overall summary here is conventional current is the direction of current from the positive end of the battery to the negative end. Electron flow is the directions of electrons move from the negative to the positive. We use this one in circuits. I can't spell. Shoot. So in engineering, this is the one that we're going to be using. Oh, crap. So in engineering, we're going to be using conventional current. I usually throw a quick question. So I would like you to copy this down. I usually throw a quick question like this into the exam at the end of the and test at the end of the topic. So I'll say, hey, is conventional current from the positive to the negative, or which way does electron flow move, or something like that? Which one do we use? Just making sure you've got this idea down. So let me just see how much time we've got left. I want to know. We've got 8 minutes or so. We've got about 9 minutes left. Yeah, you're right. Big ticks around the conventional current. Okay, so I'm going to now, in the last 8 minutes, am I going to talk about voltage? Let me see. I might finish up. I might spend 5 minutes talking about voltage, and then I might wrap it up there. I wasn't going to talk about this because I was going to talk about just current, but as you can see, the lesson goal sort of talked about conventional current, which we've done. Let's jump in. Let's jump into quickly talking about voltage. If I can talk about voltage this lesson, then that's a pretty good guess here. If I've gone too quickly, please let me know either in the chat. I might even grab the chat open. Let me know if I'm going too quick. All right. But yeah, so we've talked now how do we calculate current? We've done. Beautiful, excellent. That's our calculations of current. We've done our what current is. Current is the movement of charge. You need to have a circuit in order for current to move. Otherwise, it's like trying to rush against a blocked wall. So here's the circuit which allows it to move. You also need to have a negative to positive. You can't just make current go from negative to negative. And then we talked about electrons don't actually move that much when we have charge. The charge moves a lot. As you can see, that red dot's moving quite quickly, but the electrons don't move very much. If you follow one electron, it takes 5 times before it gets to the end. We talked about the difference between conventional current versus electron flow. They're in opposite directions. Conventional goes from positive to negative. Electrons go from negative to positive, but we use conventional current because we're engineers and that's just what we use. What I'm going to do is I'm going to spend 2 minutes talking about voltage, and then I'm going to spend the last bit showing you guys the homework that I sort of set for you guys to do. So here we go. Voltage. So this gets back to our good old guy Alexander Volta here. Voltage is the amount of force needed to move the electrons. It is also linked to the amount of energy the electrons have. It's measured in volts and has a symbol V. Thank God, because we finally get ones that make sense. The example that I normally give for voltage is I like to just get you guys to look at a picture like down here, or just to think of this. Imagine you've got some air, and then near that air you have a big rod that's got a lot of negative charge on it, and you've got another rod here which has got a lot of positive charge on it. Those electrons really want to get to that positive area, but the reason they can't is because you need to give them enough energy that they can jump through air. Air is really hard to jump through. Electrons just don't want to move through air because it's a really bad conductor. So you need to give them a lot of energy. You need to give them a lot of energy before they'll jump over. Guys, can we like leave Mr. Volta alone, thanks? You need to give them a lot of energy before they'll jump over, which means you need to give them a lot of voltage before they'll jump over. So that's why the voltage has a symbol V, is needed. I like to think about it as, okay, so you've got current, which is how much water is flowing down your stream. Voltage is how much force is in that stream. Okay, you can have a big river that is moving very slowly, and then you could have instead a really fast moving river that's just, you know, carries you away really quickly. That's the difference between voltage, is how much force you can push down that river. So what else can I quickly say? Let's see. I've got 4 minutes left. So here is the same sort of idea here. Even though in this picture, voltage, the force or the pressure, the push of the electrons, right? That push of electrons is still occurring even though the switch is closed. So here, if I then take this idea and I go, okay, when the switch tap is off, is there any pressure? Yes, there is pressure. There is a lot of force pushing on this tap here. There's a lot of force happening here. It's a big amount of force. So yes, there is a voltage. There is a big push, even though it's closed, because it really wants to get out. When the force is switched on, is there still a push? Yes, there is still a push. There is still voltage even once you open it up. So the idea is, if I have here, is there a voltage when it's switched on? The battery provides voltage that will push current through the bulb. That's the voltage that's pushing the water through. It's the voltage that's pushing those electrons around the circuit. So yeah, that's the main difference between voltage and current. I might go back over voltage a little bit later on, but yeah, that's the main difference. I'm going to stop the lesson here